Hello everyone. In today's video, we will learn about principal component analysis. What is this principal component analysis? It's a dimensionality reduction technique. So what is meant by dimension? Dimensions are nothing but those are the features, or you can say it as the predictor variables that determine a model's output. We can call them as input also, input variables also. So what is the problem with this high dimensional data set? What does it mean by high dimension? High dimension means the data set which is having more number of features. So basically for high dimensional data set, it has some practical concerns for machine learning algorithms, such as it will increase the computational time, storage space for big data, overfitting, visualization challenges, etc. So this dimensionality reduction helps to reduce the number of features while retaining key information. So what does it do is it converts the high dimensional data into a lower dimensional space while preserving the important information. So here in this diagram, you can have a look at it. Here you can see in 3-dimension, it is like 1000 positions of data, which is being converted in 2-dimension as 100 position. This is 2-dimensional data. And when it is being converted to 1-dimensional, you can see that 10 position. So from 1000 to 10, it has been reduced. This is the kind of, what we talk about dimensionality reduction. So in certain cases, when the original features are highly correlated or redundant, then we can use feature extraction. So feature extraction is nothing but it is also called as feature projection that transforms the data into a lower dimensional space by creating new features, which will be the combination of the original ones. So the principal component analysis, in short, we call it as PCA. So this projects data onto directions of maximum variance. So basically PCA identifies the direction, that is the principal components that capture the maximum variance in the data. So basically it is used for reducing the dimension while preserving as much variance as possible. So why this variance is important when we talk about PCA? So variance is nothing but it measures the spread around the mean, and features with low variance indicate little variation in their values. So this kind of features are often need subsequent analysis. Maybe it will hinder the model performance because the variance is very less. So let us see this diagram. You can see here suppose you are asked to find the height of a person. So in the figure on to the left, you can easily find who is the tallest one. But when we observe the right hand side diagram, if you are asked to find the tallest person from this diagram, it is slightly difficult because you can see there is not much variation in the height. So here in the first diagram, you can see the height difference is more, and in the second one, the height difference is less. So here you can see that on the left side, the diagram, the data is having more variance. In the second one, the data is having less variance. So basically, if the variance is more, then the decision making becomes easier. So that is why we are interested in the data which is having more variance. So in principal component analysis, actually it's a technique which was introduced in 1901 by a mathematician called as Carl Pearson. So how it works on the condition that while the data in higher dimensional space is mapped onto the data in lower dimensional space, the variance of the data in lower dimensional space should be maximum. That is when we are reducing from higher dimension to lower dimension, but the variance should be maximum. So basically it's a statistical procedure which uses orthogonal transformation. So here we have a complex set of data set. By using PCA, it can be reduced to a lower dimensional data. So basically it's a mathematical procedure that transforms a higher dimensional data into new set of variables called as principal components. So basically these components are nothing but those are the linear combination of original variables and capture the maximum amount of variance in the data. So when we find this principal components, the first principal component accounts for the most variance. Then next highest will be the second principal component, then third principal component, and the remaining. So the first principal component will be having the maximum variance. So, as I already said, it is a linear combination of original input variables that captures the dataset's maximum variance. So, we can represent it as, suppose this one, you can see here, is at 1. So, this is one linear combination of variables. So, it determines the direction of highest variability in the data. So, larger the variable captured in the first component, when the larger variability means we have the larger information captured by the component. So, the second principal component is also a linear combination which captures the remaining variance, but it won't be having as much variance as the first component. First principal component is having the maximum variance. Next variance will be the second principal component. So, basically, when we are talking about first principal component and the remaining principal components, the relation between first principal component and second principal component, they should be uncorrelated. So, we can say the correlation between first and second component should be 0, or in other words, we can say that they should be orthogonal to each other, that is perpendicular. You can see in this diagram that first principal component is having maximum variance and the second principal component is nothing but it is an orthogonal vector to the first principal component. So this is how we can represent. You can see here, this one is PC1, that is the first principal component. This is PC2, that is the second principal component. So when you talk about the variance for the first principal component, you can see the data spread. The into marked ones are the data points. So here in first principal component, you can get the maximum variance in data. Here you can see the maximum variance, but for PC2 you can see the variance is lesser than the first principal component. So basically the transformation may be from 3D to 2D or 2D to 1D. So here it is a 2D data, so we can take it to 2D to 3D. So what are the steps for PCA algorithm? So first step is to standardize the dataset. So we have to standardize the dataset. First one is standardizing dataset. Then after standardizing, we have to calculate the covariance matrix for the features in the dataset. So once the covariance matrix is found, then we can easily find the eigenvalues and eigenvectors for the covariance matrix. But once you find this eigenvalues, what you have to do is you have to sort the eigenvalues in descending order, means the highest value first. So then pick the highest pick k eigenvalues and form the matrix of eigenvectors. So first we'll be forming the covariance matrix, and from that you will be finding the eigenvalues, then we will be arranging it in the descending order, then we'll be choosing the highest value of eigenvalue, and corresponding to that eigenvalue we will be finding the eigenvector. So after that we will be transforming the original matrix. So let us consider an example here. So here there are two features, one is x, second one is y. So there are sample points here. This is 2.1, 1.5, 2 points. So here this one, this one, this one, this one, this one. So these are the sample data. So we have 5 samples for each feature. So x is one feature, y is another feature. We have 5 samples each. So what is the first step? First step is to find the mean. So how will you find the mean? So x, let us consider this x. So when you want to find the mean of this x, you sum up all the data points and divide by the total number of data points. So here you have 5 data points. You are taking the sum, that is 2.5 plus 0.5 plus 2.2 plus 1.9 plus 3.1, that divided by the total number of samples, that is 5. So you got it as 2.04. Next is to find the mean for the second feature, that is y. So we are finding that one by summing up all this value, that is 2.4 plus 0.7 plus 2.9 plus 2.2 plus 3 divided by 5, you got it as 2.24. So we found the value for mean for both the features. Next step is we have to center the data. How will you center the data? So already x is known, that is our first feature, and you have y. And we have already found x bar and y bar. So x bar is, we found it as 2.04 and y bar we found it as 2.24. So what we have to do is we have to find center the point, means x minus x bar, and we are finding y minus y bar. So for each value, for the first value we have 2.5, so 2.5 minus x bar, that is 2.04. You got this first value. Similarly, for all the x values, you are subtracting the values from the mean from the data points. So second value is 0.5 minus 2. You can see that x bar is 2.04. So you are subtracting that and finding the values. Similarly, for y also, these are the y values. So first value is 2.4. So you are subtracting that with the y main value, that is 2.24. So 2.4 minus 2.24, you got first value as 0.16. Second value is 0.7 minus 2.24, you got it as minus 1.54. Similarly, you have to find this value for all the dataset values. So for x we have found and y also we have found. So we have centered the data. What is the next step? Next step is to find the covariance matrix. So covariance matrix, how will you find? So this is the formula for finding the covariance matrix, that is summation of xi minus x bar. X bar we already found, yi minus y bar also we found. So also we have found this xi minus x bar and yi minus y bar in the previous step. Here you can see we have already found the center points divided by n minus 1. So here please note that it can be sometimes divided by n also. So n minus 1 is used when we are considering the samples, and n is used when we have the total population given. So depending upon the data set you have, whether if it is a population data set is given, then you denominator should be n. And if you are just taking a sample out of the total population, then you can use n minus 1. So here in this example, I am assuming that I am taking it as the sample point. So I have divided it with n minus 1. So what is this n? N is the total number of data points. We have 1, 2, 3, 4, 5. So n minus 1 is nothing but 5 minus 1, that is 4. So n minus 1 is equal to 4. So what is this covariance matrix? So this is a covariance matrix is C, that is represented by the entries are like this. First element is covariance XX, second one is covariance XY, then covariance YX and covariance YY. So how will you find this one? So already we have the equations for finding the covariance XY here. So for finding covariance XX, this Y we will be replacing with X. Okay. So this is the one. So covariance XX is nothing but 1 divided by n minus 1 sigma xi minus x bar. That is this first term. And then what is the second term? Second term is not y. Here again we are using x. So instead of yi minus y bar, we will be using xi minus x bar. So basically it is xi minus x bar the whole square. So here you can multiply it. So it is, what is this xi minus x bar? We have already found this. This is for first value it is 0.46. So second value it is minus 1.54. So the first value, so x1 minus x bar, that is x1 is the first value. So 0.46 into 0.46 plus, that is why this point into, so this one into this one, both are same. That is why here xi minus x, this is 0.46, this is 0.46 for the first data. For the second data, what is that one? Here we found it as minus 1.54. So minus 1.54 into minus 1.54. Third data is what? 0.16. So similarly you are multiplying it and taking the summation. So this final you are getting it as 0.9380. What is this one value you got? That is nothing but we got covariance x comma x. What is the next covariance we need to find? You need to find covariance x comma y. How will you find covariance x comma y? Use this form, the original formula. So x and y. Now what is this one? xi minus x bar. So basically what is that one? x1 minus x bar into y1 minus y bar plus x2 minus x bar into y2 minus y bar plus etc. up to x5 minus x bar into y5 minus y bar. So we found this x1 minus x bar into, so x1 is x1 minus x bar, first one, this is the first data, so 0.46 into 0.16. So the first one is 0.46 into 0.16. Second one is minus 1.54 and minus, so plus minus 1.54 into minus. Third one is here 0.16 into 0.66 plus this one minus 0.14 into minus 0.04. Third one is plus 1.06 into 1.06 into 0.76. So that is what we have got here. So this one you can see all this summation we have done. So when you are doing the summation, this is what you are getting. So covariance x comma y, we got it like this. Covariance x comma y is same as covariance y comma x. You need not find it again. So you will be getting the same answer. Next one here, so covariance y comma x is also done. Now you have to find covariance y comma y. So what is this covariance y comma y? So the both terms are in y. So y1 minus y bar into, so it will be y1 minus y bar into y, it is whole square, we can say, plus y2 minus y bar whole square plus etc. So here this is the whole square, y1 minus, you can see here, this is the one, this is the one value 0.16. Then second one is this one minus 1.54, then 0.6 is 0.04 and 0.76. So this values only the square we have taken. So we got the value like this. So now we got the value of covariance xx, covariance xy, then covariance yy. So all these values we got it. So now we can form the covariance matrix. So what is this covariance matrix? Covariance matrix is covariance xx, covariance xy, covariance yx. So this all values we have found in the previous step. So what is that covariance xx? We got it as, we'll just go back, covariance xx we got it as 0.9380. What is covariance xy? We got it as 0.8405. So we have written that, substituted those values, we got this matrix. So once we get this matrix, what is the next step? Next step is to find the eigenvalues. So in my previous video, I have explained how to find eigenvalues and eigenvectors. So here for finding eigenvalues, so this matrix is C. So this is the matrix C. So we can use the formula C minus lambda I is equal to 0. So here it is a 2 by 2 matrix. So we are taking identity matrix lambda I. We got it like this. Then what we have to do? We have to subtract it. So we got this matrix like this. Simplify it. You will be getting a quadratic equation like this. Now once you get the quadratic equation in lambda, you have to solve for the roots. What are the roots? The roots are nothing but those are the eigenvalues. So these are the eigenvalues. You got two eigenvalues, lambda 1 and lambda 2. Now what you have to do is you have to arrange this eigenvalues in descending order, means highest value first. Now first value is 1.7371. Second value is 0.0539. This is by default, it is the highest value is coming first. So it is 1.7371 when you are arranging. So it is 0.0539. So out of this, the highest value you have to choose for finding. So this is the highest value, 1.7371 is the highest value of eigenvalue, and we'll be finding the eigenvector corresponding to this eigenvalue of 1.7371. So next is we are going to find the eigenvector for the largest eigenvalue. So what is that formula we have already studied? A V is equal to lambda V. So instead of A, we have the matrix as C. So this is the equation we are going to use, and for lambda we are using lambda 1 because lambda 1 is the highest value out of those two eigenvalues. So V is nothing but V1, V2. So we are using the equation C minus lambda I into, so this equation is converted to this because you have taken lambda I to the other left hand side. So when you're taking lambda to left hand side, you got this equation C minus lambda 1 I into V is equal to 0. So this is the equation we of this matrix we already have. So instead of lambda, what is this equation? This equation we were already having. So instead of this lambda, we are substituting lambda 1. So we have substituted lambda 1. So lambda 1 value, you know, it is 1.7371. So we have substituted that value here. So 0.9380 minus 1.7371 gives you this one minus 0.7991. Similarly, here also 0.8530 minus lambda 1, you are getting it as 0.8841 minus. So this is the equation you are getting. So you just multiply this one, you will be getting two simultaneous equation. One is this one. So 0.7991 into V1 plus 0.8405 V2. This is the first equation and this is the second equation. So just consider the first equation. So you can express one variable, this one in terms of any one variable. So V2 we are expressing in terms of V1. So when you are taking this minus 0.799 V1 to the other side, you got the equation like this. So V2 is nothing but 0.799 divided by 0.8405 V1. So that is nothing but 0.9507 V1. So V2 is equal to 0.9507 V1. So let us assume V1 is equal to 1. So when you are substituting V1 is equal to 1, we will be getting V2 as 0.9507. So we can directly write the vector as 1, that is V1. We know that V is equal to V1 and V2. So V1 we have taken it as 1. So V2 is 0.9507. You are substituting this, you got like this. So once you get this eigenvectors, ideally you need to normalize it, because to make the magnitude 1, so we are normalizing this vector. So I will normalize this one. So that is nothing but this square plus this square summation. So that is what is done here. Square root of 1 square plus 0.9507 whole square. That is equal to square root of, so you are getting the value as this one. This is the normalized norm of V. You got it like that. So in this vector, you divide each value with this norm. So you will be getting the normalized value. So 1.9507 you are dividing with 1.3796. So this is after dividing with this 1 and 0.9507 divided. You are dividing with 1.3796. You are getting the values as 0.724 and 0.689. So this is nothing but this is the first principal component. Why it's a first principal component? Because it is corresponding to the highest eigenvalue. That means it represents the highest variance. So second eigenvector, you need not find it, because we already our dimension is 2 and we are interested in reducing it to 1 dimension. So second eigenvector is not required, but I have just mentioned here. If you want to calculate, you can calculate. This is the final value of second eigenvector. This first, once you find this eigenvectors, the next step is to project the center data onto the first principal component. So this is what is we have to transform. So projection is given by the formula. So you just notice these two formulas I have written. So it can be either U transpose X or it can be XU. It depends upon how your data set is there. So if the samples are represented in column wise, then you can use this formula, and if the samples are represented by row wise, then you can this formula. But in our example, you can see that the samples are column wise, because you can see the feature is here, the first sample is here, second, 3, 4, 5. You can see these are all column wise. So we can use this formula. Okay, you can use this formula. The first formula we can use it, because we have the samples as column. So now what is this X? X is nothing but the center data. This is capital X. So this is the center data. That is xi minus x bar, yi minus y bar. We already found these values. So this value also we have found, this value also we have found in the previous step. You can see here, in this step we have found that this one is x minus x bar, y minus y. Basically it is xi minus x bar. This is yi minus y bar. So you won't get confused. So these are the values you are getting here. So these two values we found, this 2, 1. Then what is the next one? So we have to transform. So projection is Z is equal to U transpose X. So X is nothing but this is we are getting from here, and this U transpose is what in the previous step we found. This one is our U. So this is our U. So first eigenvector, that is the eigenvector which we have found, that is this U. So what you have to do is you have to multiply this U transpose we are taking. So that was a column vector. So we have taken the transpose, it became row vector into X. So this is our Xi minus, this is Xi minus X bar, and this one is Yi minus Y bar. So both the values are there. So then you have to multiply this one with this. So when you are multiplying, you will be getting, let us consider separately. So 0.724 into first value, that is into this into this plus this into this. So you got the value as this. Similarly, second column you have to take second column, that is 0.724 into minus 1.54 plus 0.689 into 1.54. Third one, 0.724 into 0.16 plus 0.689 into 0.66. So similarly you are finding for all other columns, you got these values there. So this is our X minus X bar, that is the centered value. This is Y minus Y bar, and now we have found this projected value Z. So these are the values, that is what we have, 0.44328, that is first value, minus 2.17608, that is from here. So all the values we are getting here. So now if you observe this, here the two features, now here this is one feature, this was another feature. Now you got so two features has been reduced to single dimension here. So this is how the principal component analysis in a higher dimension, it has been reduced to a lower dimension. One more thing you need to understand is how the variance is being taken care of. I was talking about the first principal component represents the maximum variance. I'll show that also. So eigenvalues are nothing but those represents the variance of principal component. So the total variance is nothing but lambda 1 plus lambda 2. What are those lambdas? Lambdas are our eigenvalues. So we found the eigenvalues as these two values, 1.7371 and 0.0539. So this is what the value we got, the sum of both the eigenvalues. So the fraction explained by principal component is this one. Principal component is corresponding to the first eigenvalue. So 1.7, you have to divide that with the total. So 1.7371 divided by 1.791, you got it as 97%. So this 97% is nothing but the first principal component explains 97% of the variance. So that is the meaning of it. So we have seen this. So this is actually the reduced dimension. So when you are using the principal component analysis, this is what you are supposed to get as the answer. So I hope you understood how to use principal component analysis to reduce the dimension. Thanks for watching. Thank you. Please subscribe for more updates. Thank you all.